So all average rate of change is for any function, you take 2 points, these ones perhaps, and you have to imagine yourself drawing an imaginary line between them, and the average rate of change is just the slope of that line. So maybe you would label it as m if you remember from your equation of a line, y equals mx plus b. Yeah, so it's just the slope of that little line right there. And what I've done here is, instead of writing f of x1 and f of x2, I just wrote this x coordinate in terms of this one. The plus h is really just the number of units away this x is from this x. So that's just another way of writing it in terms of this one. So right here I've just brought up the little equation that we use to find the slope of a line. And what I've done right here in this box is I've replaced the y2s and the y1s with the y's that we established in that other slide. And down here in the denominator, it's just the difference in x's. So obviously the difference in this x as opposed to this x, it's just that plus h right there. So difference in x's is just h, and that's how I got this little formula right here. The problem with the average rate of change, though, is that sometimes I want to find the exact rate of change, the instantaneous rate of change at this point right here, like the one in purple. But with average rate of change, I'm always going to need like 2 points, such as this purple point and this blue one, the purple point and this blue one and this blue one. I can keep drawing lines that get closer and closer, and I can keep doing that forever, but I'm never gonna exactly get the instantaneous rate of change at this purple point right here with the average rate of change. It's just not gonna work. Now the derivative is what we want for instantaneous rate of change. So in this picture right here, we have f prime of x. That's how you say it, f prime of x. And this apostrophe right here, that it's pretty hard to see, but that's what makes the difference. It distinguishes it between f prime of x and f of x. And again, instantaneous rate of change. And imagine this as this line right here, this orange one, as a tangent to f of x at this point right here, the purple one. Now what a tangent does is it hits the function f of x at exactly this one point. No other like points, not any of these ones, just this point. And we take the slope of this line right here, and that's what gives us the instantaneous rate of change at this x right here. And again, it gives us the slope at that point. Okay, in this example right here, they give you the function f of x. F of x is equal to x squared. And they want you to find f prime of 3. And notice that little apostrophe again. It's kind of hard to see, but that signals that you're looking for the rate of change, the instantaneous rate of change at when x equals 3. Okay, so what I've done here is I've set a limit for h going to 0, and this right here is just the average rate of change formula. So why I'm doing this, this h to 0, is because the average rate of change formula just keeps using 2 points. We want that usage of 2 points to stop. We want it to approach the instantaneous rate of change of that 1 point. I think in the previous problem it was f prime of 3 that we're looking for. So we want just that 1 point, or we want a function that gives us just the instantaneous rate of change at one individual point. So what we're going to do here is we're going to try to solve this limit. And by doing that, we're going to have to do some algebra. So the function f of x from before was f of x equals x squared, right? So we're going to have to square each of these, and we're going to see if we can get any cancellations and simplify. So f of x plus h, that's going to be this quantity squared, right? Because that's the f of x formula. So we're going to write down x squared plus 2xh plus h squared. This is just algebra. And f of x is just minus x squared. Let me put parentheses. Okay, and this whole thing is over an h. And now you can see that these cancel out, the x squareds. So we can simplify this to 2xh plus h squared, this whole quantity, over h. And then you can probably see that we can factor out an h between these two terms. So that's going to be h parentheses 2x plus h, this whole quantity, over h. And now we can cancel these h's out, and we're going to be left with the limit as h goes to 0 for the, right here, 2x plus h. And since this is a limit h going to 0, this is obviously just going to be 0. And we're going to be left with, let's do a better color, we're going to be left with just 2x. So this is f prime of x. This is the formula for f prime of x. So we just found the formula for f prime of x, and that we found is equal to 2x. So again, this formula right here, it gives us the instantaneous rate of change for the function f of x. It gives us the instantaneous rate of change at every x, and technically every real x. So since the problem asked us to find f prime of 3, all we do is just substitute 3 into the equation we just found. So that's just going to be equal to 2 times 3. And so f prime of 3 equals 6, and that's our answer. So that's how you can find a derivative of a function. That was a pretty good example of one right here. But it's just going to get harder from here, and using the limit way of finding derivatives, it's not the fastest way. Maybe in a future video I'll show you how to find the shortcuts or how to use them. There are lots of shortcuts to find derivatives. This is not the only way. Limits are actually, that might be the longer way of finding them. So thank you for watching this video, and I hope to see you next time. Bye-bye.